Hey everyone, welcome to this explainer. We hear buzzwords like environmental footprint all the time, right? But honestly, how do scientists actually measure that without, well, just totally guessing? Today, we're decoding the actual, strict scientific process behind this. It's called life cycle impact assessment. So let's just jump right in and see how researchers take a mountain of overwhelming data and turn it into real, standardized environmental science. Okay, here's our structural roadmap for today. We'll start with 1, making sense of raw data. Then 2, the flawed early methods. 3, the ISO gold standard. 4, adding context with normalization. 5, the danger of waiting. And finally, 6, midpoints versus endpoints. So that brings us to the core question. Look, it's pretty easy to point out a factory and say, hey, it releases X amount of gas or uses Y gallons of water. But honestly, a massive list of emissions means absolutely nothing without a solid scientific methodology to translate all that raw data into actual real-world consequences. We literally need a system. Which takes us to Section 1, making sense of raw data. So when an assessment kicks off, researchers compile what's called a life cycle inventory, or LCI. And this gives us a colossal amount of raw data. I mean, we're talking sometimes thousands of individual data points just on resource consumption, energy demand, chemical emissions, the whole shebang. But here's the thing, raw data isn't a final answer. A giant spreadsheet is, frankly, pretty useless on its own. It desperately demands aggregation. Think about it. If a product uses way less energy but emits a super toxic substance in tiny amounts, we can't just eyeball the raw numbers and know if it's ecologically better or worse than a competing product. We desperately need a way to aggregate and interpret all these numbers. Now let's look at Section 2, the flawed early methods. Looking back at history, the 1980s gave us the Swiss critical volume method, which attempted this, honestly, kind of bizarre visual trick. The idea was to calculate the exact volume of pure air or water you'd need to dilute a pollutant down to its legal threshold limit. Just picture that for a second. Imagine trying to visualize diluting a factory's smog with giant, hypothetical cubes of pure mountain air. They'd add up all these hypothetical volumes into a single bar chart for easy comparison. It was clever, for sure, but also a slightly absurd attempt at making data readable. Unsurprisingly, the method totally collapsed, and it is absolutely crucial to understand why. First off, it relied heavily on limit values that were based on political feasibility or, what was economically desirable rather than pure science. Second, these limits varied wildly from country to country, so global comparisons were just impossible. And worst of all, it totally ignored massive ecological threats. Because limit values back then focused strictly on human toxicity, ecological threats like carbon dioxide had literally no legal limit. So under the system, CO2 wasn't evaluated at all. Yeah, a massive, massive blind spot. Thankfully, that historical failure paved the way for modern science. Section 3, the ISO gold standard. To fix those old errors, the globally recognized ISO 14040 and 14044 standards were created. The crucial point here is that this modern framework demands 3 strictly mandatory, purely scientific steps to make sure we aren't just making subjective guesses anymore. You absolutely must perform the selection of your impact categories, the classification of your inventory results into those categories, and finally, the characterization of those results into common units. And this visual brilliantly illustrates the core engine of that ISO process. Over on the far left, you've got isolated inventory results, things like sulfur dioxide, nitrogen oxides, methane. In the classification stage, they're actively sorted based on the actual effect they have. So methane and nitrous oxide get assigned to climate change. Then we move to the characterization phase. Here, specialized models apply a mathematical factor to convert these completely different gases into a shared unit, like global warming potential or kilograms of CO2 equivalents. It's a real game changer because it scientifically lets us combine completely different chemical emissions into one coherent indicator. Now notice how these distinct emissions are grouped here. They're first sorted into standardized midpoints categories. These are things we can directly measure, like global warming, human toxicity, or aquatic acidification. And ultimately, these midpoints feed into much larger, more conceptual damage categories, like climate change, human health, or quality of ecosystems. This highly structured methodology, that is exactly what keeps modern environmental analysis strictly objective. But once we have those numbers, how do we actually wrap our heads around their scale? That brings us to Section 4, adding context with normalization. So the ISO standard does include a few optional elements, and normalization is arguably one of the most helpful. Look, even if we know a product creates, say, 500 kilograms of CO2 equivalents, the average person, heck, even most scientists, need to know if that's actually a significant amount. Normalization solves this by comparing the result to real-world reference data. It's kind of like knowing a car costs $50,000. You really only know if that's expensive when you compare it to the average national income, right? Normalization gives us that exact comparative significance. To put that into perspective, researchers might use a huge reference number like 1.017 billion tons. That was the actual measured annual release of CO2 equivalents for the entire nation of Germany in 2003. So by dividing a single product's footprint by this massive national load, researchers get a specific dimensionless number. What does that mean? It reveals exactly what microscopic fraction of an entire nation's total annual pollution that one single product system is responsible for. It instantly grounds all that raw data in a sense of true comparative scale. However, taking this simplification too far leads to some major problems. Section 5. The danger of waiting. Now, waiting is another optional step, but man, it is highly controversial. The formal definition tells us exactly why. It uses numerical factors based on value choices. Let's be real. Deciding whether climate change is 20% worse than human toxicity or vice versa is not a mathematical equation. It's a human, political, and social choice. Waiting is exactly where objective science ends and human subjectivity begins. Because of this, the ISO standard strictly prohibits the use of waiting for any comparative assertions that are released to the public. The science literally has to remain neutral. Let's pull back a bit for our final section. Section 6, Midpoints versus Endpoints. We're looking at the fascinating tension here between what we can physically calculate and what we actually worry about. This perfectly maps the journey from a known cause to a highly complex effect. You can see the midpoint indicator sitting firmly right in the center. But out to the right, you see this sprawling, interconnected web of dashed lines pointing toward the category endpoints. Those endpoints represent the actual, real-world damage, the ultimate consequences of those emissions. Think of it like speeding in a car. The midpoint is your speedometer reading, highly measurable, right there, close to the source. In environmental terms, that's like measuring a greenhouse gas absorbing infrared radiation up in the atmosphere. The endpoint, on the other hand, is the likelihood of a multi-car crash 10 miles down the road. That's obviously what we want to prevent, but it's incredibly uncertain to predict. Endpoints are things like melting glaciers, sea level rise, or the extinction of specific species. They are our ultimate fear, but they're incredibly distant from the source. And this is exactly why the best science prefers to measure at the midpoint, keeping the assessment as mathematically accurate as possible. Now, consider this. 40 years ago, carbon dioxide wasn't even evaluated as an ecological threat. Crazy, right? That really makes you wonder, what new, currently undiscovered impacts will future scientists have to integrate into these ISO standards tomorrow? I mean, if we don't yet know all the complex endpoints of the chemicals and processes we use today, our environmental impact assessments must continuously adapt. It's a powerful reminder that true scientific understanding is an ongoing journey. Keep exploring, keep questioning, and I'll catch you in our next explainer.